So indeed, so what I'm going to be talking about, I mean, I was on and off for that long period of time, and I mean, it all started actually when I was doing my PhD at the Kurchatov Institute a long time ago. Well, I guess my first paper on drift waves with Mikhailovsky, and then I switched on to the sort of team with work with Zakharov, who was my PhD advisor, Sasha Balk, and then so the most recently, okay, so I've been working with Colm Connaughton, who is at Warwick now, and Brenda Quinn, who is just there right now, and she's marked here in red because I mean she's finishing her PhD and she's looking for a postdoc position. So if you liked what you see, that I mean a lot of the numerics, you know, that's thanks to Brenda's work. Okay, so now, well, sort of these kind of pictures are sometimes mentioned, shown together, geophysical applications like giant, well, not quite giant planets, atmospheres. Yes, so there were some missions of Voyager and stuff like that. So, and the tokamaks. So for a reason, because I mean it was noticed a long time ago, they have common linear and nonlinear properties, analogies that could be summed up in a minimal model, so-called Charny-Hasegawa-Mima (CHM) equation. So found first by Charny in end of 40s in meteorology and atmospheric fluid dynamics, and then by Hasegawa and Mima derived for drift waves in plasma. So, I mean, I'm sure it's familiar to all of you. So, and just very briefly to refresh, you know, that psi in this case is in geophysical context would be the stream function, which is electrostatic potential in plasmas, which is also a stream function because E cross B dominant velocity. So, rho deformation radius called Rossby deformation radius in GFD. And ion-Larmor radius, actually, ion-Larmor measured by electrons temperature in plasmas, because in derivation of this model, it was assumed that ions are cold and electrons are warm.
So ion sound.
Exactly, yeah. So the sort of yes. So same way as you would estimate speed of ion sound wave.
Physically, what is the deformation radius?
So you mean in GFD? In atmospheres it would be like 1,000 kilometers, and in oceans it would be about 100 kilometers.
What is it?
What is special? I mean, basically, if well, in GFD. You derive equations as based on shallow water approximation, very shallow fluid, and if you sort of well, the bottom is fixed, flat, and the top, okay, you can do two things. You can either leave it as a free surface or put a rigid lid. If you did put a rigid lid, right, it would correspond to neglecting this term with respect to that term. Then you would get purely two-dimensional motion. But then if it is not, so basically deformation radius define the scale at which the fact that the top surface is actually free and not rigid start making difference in the dynamics. I mean, yeah.
But isn't it just that you replace the cyclotron frequency from the amino radius by something related to the Earth rotation? The correlation?
Yes, there is, of course. Yes, exactly. So. That is the analogy, of course, here is rotation frequency analogous to magnetic field, and the Coriolis for the gradient in Coriolis force is analogous to gradient in plasma concentration that leads to so-called beta effect in GFD, or drift velocity in plasmas. Okay, so basically it's gradient of potential vorticity. So the gradient of potential vorticity in GOD arises from the fact that you have Earth is round and rotation. So you're using kind of so-called beta plane approximation local on the sphere, right? And rotation frequency, what matters is the sort of projection of rotation frequency on the perpendicular direction perpendicular to your beta plane, and that because and so this equal to rotation speed times cosine of the azimuthal the poloidal angle, and because it changes across the plane, so you get the change in sort of a gradient of potential vorticity. So, so this is similar effect as, well, similar, yeah, so it plays similar role as change in plasma concentration. So directions is kind of important because it's been precisely the opposite in GFD to the plasma. So X is considered east-west. And Y is south-north, right? So X is poloidal arc length and Y is radial length, right? So this is, of course, in the plasma convention, it's the totally the opposite, right? So you would switch X and Y here. So you would put here Y normally in Hasegawa-Mima equations. But I've been, giving this talk to sometimes to plasma or sometimes GFD communities, and just being a bit lazy. So if you're uncomfortable, so you just need to turn your head like that if you see XY, KX, KY graph, and to see a familiar picture, So zonal flows are typical, obviously, for both systems then. So they are very prominent on giant planets, for example, and so in plasmas, as you all know, and and what is being discussed as a paradigm for LH transitions, of course, is that small scales generated by instability will then create zonal flows. Zonal flows will suppress the waves that generated them, and that and because small scales contribute to transport and zonal flows presumably don't, so we have suppression of transport, creation of transport barriers, LH transition. So zonal flows also seen not only on giant planets but in atmospheres of Earth, and in oceans, there's plenty of them that have been discovered relatively recently when the resolutions was cranked up.
What's the color here?
The color is vorticity. So
But this is a simulation.
it's a simulation, and that's how it was discovered by recently. So when resolution actually increased in simulations, Earth simulator center here. So this is and similar were obtained in other centers. So one started seeing very clearly zonal jets. So this is not so. This is relatively obtained in relatively recent years. And about the LH transitions in GFD, so it's actually been discussed. It's called. It's been discussed, and it's even called has its name, barotropic governor. So it was discussed in paper of James and Gray, 86, and then James went and wrote more about it. You can see a very similar diagram that is normally plotted by people in plasma, right? So to describe this paradigm of zonal flow drift wave, right? So that was done by these guys, okay, so in paper of James of 87. So differential heating, so in your case, gradient of temperature or pressure leading to instability, right? That will pump energy into the, what is AZ? Potential available energy, AZ it's called. Okay, and that will, via instability, it will create kinetic energy, right? Kinetic eddy energy, and which is more or less small-scale waves. That's called baroclinic instability. So, which is in many ways equivalent of ITG or of other instabilities in plasma. So that will then transfer its energy to the kinetic energy of zonal component, right? There will be drag on both eddies and on zonal component that will drag a bit. But zonal flow, so what's important, you see this handle that squeezes the transfer, creates a negative feedback loop, and saturates the stops the instability by zonal flow. So LH transition in atmospheres, if you wish. So now in my talk, I will discuss, well, basically some of the things that of these things I came across or stumbled across, while doing my PhD, using description called wave turbulence. Use kinetic equation for drift waves, and in particular the feedback mechanism of generation of zonal flows and suppression of them. And that, of course, the kinetic equation itself was derived from a CHM model. And and it was speculated that this mechanism will be like that. But I always planned and to do some numerics, and I felt uncomfortable that actually, a lot of the predictions remain speculation. So it's okay to offer it as a paradigm, but I thought it's important to come back to a basic model, right, to a minimal model, and actually to test very carefully whether what was speculated actually is happening or not. And so, therefore, in the recent maybe 5 years or so, myself and my collaborators came back to that and examined that predominantly numerically using a CHM model. So what I'll tell you about, there will be like 3 parts, but I'll keep it short. Okay, so basically, first part will be about the anisotropic inverse cascade, how it generates zonal flows. Second, about modulational stability, how it generates zonal flows, right? And there is interplay that could be considered as a view from different angles of the same mechanism. But factually, there are essential differences, local versus non-local transfer. And in part 3, I'll talk about the feedback of zonal flow onto the turbulence and suppression of turbulence, and which you can call LH transition. If you want, you can put quotes around it because it's a very simple model. So, first of all, okay, so generation of zonal flows by inverse cascades. And here, just a very brief reminder about where inverse cascades concept is coming from. It's coming from 2D classical turbulence, right? Which, of course, can be obtained from CHM by crossing out these 2 terms, right? Which means that the nonlinearity has to be big enough for this linear term not to be important. And as I said, you put rigid lid on your or consider scales short enough for this term to be unimportant.
So I guess in the fusion context, we're normally thinking about that del squared term as small.
Yes, yes. So I'm just.
Yes, that has nothing to do with
Yeah, yes. No, this is true. Yes, I mean I'm talking about here just for the sake of illustration, right? So I'll come back to. Of course, I'm not going to cross them out from now on, as they say, but I mean I'll come back to that. So then the system will have two conservation laws of, called energy and entropy, right? Which also exist in CHM. And both of them, according to the argument, ingenious argument suggested by Fjordov in 1953, they must cascade in the opposite directions. So the argument, which I'm not going to go through, it's kind of like, I'm pretty sure elementary for all of you here in this room. So we know, so this is the inverse cascade of energy. And now we come back to the CHM model. So now here, first of all, important to introduce a scale where one can cross this term out or leave it, or when it is going to be important. And that's called the Rhine scale. So the Rhine scale basically estimated like this. So suppose you do have inverse cascade of energy, right? So called Kreising cascade. And and then based on it, you estimate the time scale, characteristic time scale in the problem. And then you compare this time scale with time scale arising from a linear term, right? And the balance will give you this characteristic wave number. Okay, basically, if you now then take into account that the system is anisotropic, right? Kx and ky are different. In k space, you're going to have these two lobes, and so this is called lazy 8 or sometimes dumbbell figure. And so this is where. So outside of that, we have strong turbulence. Beta can be ignored. And inside of that will be weak turbulence. So linear terms will dominate over nonlinear ones, right? And the zonal scale will be here. So again, if you're not used to that, it should look like that. So
Why is it
lazy 8 because it's like that. It's sleeping. Yeah. It's a Greg Holloway's name.
You just redefined Y and X, it would become an active like alert.
That's why I decided not to, because then it will entail the whole thing, change of terminology. Nobody would recognize it anymore, right? So
No, X is actually Y.
yeah, exactly. So,
So GOT people are lazy and fusion people are
yeah, right. Yes. Yeah. So, and yes, some people are strong, some people are weak, right? So outside of that, we have strong turbulence, and weak turbulence will be inside of that. And basically here, it's, if you wish to put it in a familiar language, it will be critical balance. Right? So linear term balance is nonlinear at these particular wave numbers. Okay, so now talking about weak turbulence, right? So there's been a prediction about the extra invariant for CHM. Okay, invariant that we call zonostrophy because it helps creation zonal flow. So it has to do with rotation and zonal, so it's zonostrophy, right? So here it is. So the conditions for this invariant, basically this invariant is a precise conservation law for the kinetic equation, but kinetic equation is obtained under two assumptions: weak nonlinearity and random phases. And so both are important for conservation of this. So basically in the original CHM system, it will be adiabatic invariant. But phases might conspire to get not random and correlated, and therefore it wasn't too clear until we checked it numerically how well it is conserved, right? So we thought it was important to check its conservation. Yeah.
So kx and ky enter into this in a non-symmetric ways? Presumably that
Has to do with beta.
term,
Yeah.
So why is there no beta in this expression?
There is no?
There's no beta in this expression.
No, because, well, okay, so here, well, yes, there is no beta in this expression, and even in more general, you can write a more general expression for arbitrary rho, and there will be still no beta, and that's
if
good.
I set beta to, so isn't this counterintuitive?
This is actually quite, yes, interesting. So I don't know. So you set beta to 0. So, okay. I don't think you can do that. But I mean, let me kind of postpone this question and think about it. So there is no beta in it. That's for sure. You know.
Well,
But there is rho. Okay.
Perhaps it has something to do with direction. I mean, with beta, it's an anisotropic equation, so maybe energy flows or something in k-space in some particular.
Yeah, but you know, phi. There's phi. in
I
this
understand.
equation.
I don't understand it. I don't understand it either. But I mean, just speculating. There's obviously something about directionality.
Yes.
In the basic assumption.
So we will we'll talk about direction of cascades. That's precisely why I'm introducing that, because I mean I will see we will see how it makes the cascades.
In other words, so you're saying that if I took this equation and plugged that
In the kinetic equation, it will be conserved.
No, in the CHM equation that this is going to be conserved.
That we don't know. I mean, because it's an exact invariant of the kinetic equation, right? So to what extent it then carries its conservation property to the.
So it's not it's not like energy.
It's not like energy, and so it's I would say it's an adiabatic invariant that arises at a certain weak nonlinearity, but also some sort of phase randomness too. Okay, so that's why we thought it's important to do numerics and see what it does.
What? Beta must be not there because it's large, because it's only for the weak turbulence.
Yes, so it's kind of limit beta.
It's the beta infinity.
Yeah, it's yes, exactly. So I suppose beta just only comes into the time scale. In that it can be scaled out, in this kind of three-wave interaction approach. Right, but I mean, why I mentioned this here, because now we have three positive invariants, right? Positive, quadratic, and we then they both should be transferred in k-space, right? And we can, first of all, straight away make a trivial observation that three cascades cannot be isotropic in k-space, right? So you can't divide k-space in three parts, in three sectors, so that it would be isotropic. The only way to divide it is mod k greater than something, mod k less than something. That is the only way, right? So, but it's only two, okay? And so so it will be anisotropic. So let's now repeat Fjordov argument by sort of in this idealized setting, kind of a classical Kolmogorov-like setting. So but now it's isotropic setting. So I have in Fourier space, I create turbulence around some scale that I mark with plus, right? And then I dissipate it somewhere very far away from that scale, right, in all directions. So I surround it by a ring, inertial interval, which is a ring, right? So which is neither dissipation nor forcing is present in here, right? So and then I ask in which part of this dissipation scales can these three respective invariants be dissipated, right? So this is a kind of statement of.
Where is k equals 1 in that picture?
There is no k equal to 1. I mean, I'm sorry, I'm right now, I'm discussing this case, but I.
Okay, that's fine.
Yes, but I mean, I know you don't like it. I mean, we'll come back to.
I'm just trying to
Yes, we will come back to the case with rho finite. So it's just in cases in order to get a nice Firtaov argument, I need scale invariant expression, and in order to do that, I either take a large K limit or small K limit. Okay, and I happen to take large K limit here. Okay, so 3 invariants, right? And basically, it's if you think a little bit yourself about Firtaov argument, you will recognize that basically the boundaries between the sectors where different invariants cascade are determined simply by equating by pairwise equation of their respective k-space densities, right? So equate these two, and you'll get boundary between the energy and entropy cascades. Equate these two, it will be a boundary between the entropy and zonostrophy cascade, okay, and so on. And so basically, if you do that, then you very simply obtain that this picture that you see, like before, the entropy must cascade to logic. So this picture is, by the way, kx and k, mod k, right? Okay, so z has to cascade to large wave numbers as before, energy to smaller wave numbers. But you see, there's a big sector in k-space that is eaten out by this extra invariant, right? That pushes energy towards zonal scales, right? Energy not only cascading to smaller k's, but also it's bound by this very steep curve asymptotically, cubic root of kx, right? So it's really, as it goes to smaller k, it must really get funnel itself into very, very zonal situations. Right, and so let's do some numerics on CHM model with a spectral method. And we start with an initial spectrum that has a Gaussian blob around this scale, right? To correspond to our picture, to check picture cascades that we develop. And then we are going to track the invariants, 3 invariants, by tracking the centroids, right? Basically, we just weigh their corresponding densities, okay, and so there will be energy containing wave number, or sometimes called the integral scale of turbulence, the potential centroid and the zonostrophy centroid, okay. They will be functions of time, and we'll follow where they go, right?
Why is this choice? What is behind the choice? Something like, why do you divide by
This is a normalization, right? So basically, you see, this is the density of energy, right? You weigh wave number with energy density and divide by total energy. So this is just the definition of the energy containing scale, right? And so on, so here. So, and let's do numerics, right? And first of all, we do weak different levels of nonlinearities. First of all, let's consider weak nonlinear run, where basically we're quite deep inside this lazy 8. We are in weakly nonlinear regime with our initial conditions. And so we see the energy is perfectly conserved. The entropy sinks like that, as it always does in simulations like that, because your entropy cascade is forward, and at some point you reach discretization and blah. So the small scale dynamics is not well described at some point. Now look here. This is in green. This is zonostrophy, right? So this invariant is quite well conserved in this case, as you can see, right? You can see tiny sort of fluctuations fast, but they kind of cancel themselves, so cumulatively it's quite well conserved. And for comparison, we just put some quantity that's not supposed to be conserved, psi squared. Why? Because if dynamics is weakly nonlinear, right, anything will be conserved asymptotically if nonlinearity is small, right? Because the nonlinearity is 0, everything is not evolving, right? So we need to be able to compare true conservation with something that arises for trivial reason of nonlinearity being small, right?
Dissipation in this system.
There is no dissipation here that we've chosen
So
to.
you're pumping energy, or is it an initial?
No, initial blob, and we let it
So
evolve.
initial block.
Yeah.
So why is psi? I see.
And psi shouldn't be conserved. It's just some arbitrary quantity that, and it's not conserved, right? So it just goes up.
You can't go up forever if you have some.
Well, it can, because energy is, it's not energy, right? So,
It's a thing, but you have finite resolution,
yes.
and you have.
No, of course
some
we're
initial
not going
condition.
to consider till infinity, right? When we reach maximum resolution, we stop simulation, because beyond that, there's no point talking about cascades, right?
So this is all basically just the scale of psi being refined, and this somehow resulting in psi squared going up.
Scale of psi being what do you mean, refined?
Well, I'm just wondering, you started with a certain amount of.
Probably actually
and then
psi going along with
it's inverse cascade or something like that.
Yeah.
Oh, I
Yeah.
see.
This
That's
is true.
not going to go on forever. Presumably, if you run this forever.
Then it will go
this-
to some
this
sort of
will stop.
thermodynamic
It will
equipartition.
stop.
Yes,
Stop
they
it.
will all stop, and they will all be kind of describing just relay genes kind of distribution. Okay.
Have you actually done that just as a test of the code to see that we get the proper equilibrium?
We haven't. It can be easily done, of course. Yeah. Of course, equilibrium is an interesting question in itself. We know that if PU, there is no equilibrium, even though it was expected, right? So, who knows in these systems? Well, although in CHM, of course, it was done as in 2D Euler in the beginning of turbulence era, so, it does go to this, but I guess 5 Montgomery, they had the papers like that. So, right, so now let's see the centroids, what they're doing. So we see all 3 invariants, right? So cascade in their predicted sectors: entropy, zonostrophy, and energy. Somehow energy.
Oh, the colors are all crazy.
This is.
Oh, I got it.
Yeah. Okay. The thing is, the trajectories are crazy, not colors,
No,
right?
I just thought you pointed to the wrong one.
Oh, I see. Okay, so basically the trajectories have a lot of sort of oscillation, recursion, very noisy, right? That is factor related with weak nonlinearity. Okay. What's interesting also that energy actually goes on the boundary of its predicted range, so it can go deeply inside, but Fjordov argument deals with strong inequalities, and it allows going along the boundary too. So it's not a contradiction with Fjordov argument, right? So
and is the blue thing wanting to go on the other boundary, or is it just?
no, okay. Look, the other boundaries, in fact, is just this is mod k, this is kx. Here it doesn't exist, right? Mod k cannot be less than kx. Yeah. So this is just this representation. Yeah. Okay, so now strong and for strong nonlinearity, okay, we're basically strong, meaning we're on the side of the dumbbell, right? We don't want to go much way outside, because then it is going to be just usual isotropic 2D turbulence without beta effect, and that's already been studied, and we want to know effect of basically beta effect, right? So that's why we start kind of on critical balance. Okay, and we see that initially energy and entropy behave as before, but zonostrophy sort of initially it's not conserved, but then it kind of strangely levels out, and so over the rest 2/3 of the computation it kind of is conserved. So the interpretation, our interpretation is that actually zonostrophy supporting scales are getting the inside the dumbbell during the evolution, and they become weakly nonlinear. doesn't mean that the system is becoming weakly nonlinear, because entropy cascades to higher wave numbers where they are strongly nonlinear, right? It's just this particular invariant is supported by weakly nonlinear scales. But if it is, then it's conserved, and then it's enough for Fjordov argument to work again. And there is no surprise, then it does work. Okay, so you see entropy cascading here, anisotropy and energy. Okay, now slightly off this, but again, I mean, this is a fuzzy boundary. This is only Fjordov argument only works with much greater or much less kind of inequality. So it still, you know, goes more or less along this boundary, right? So the energy. So, and you also can see there is much less fuzziness of the trajectory. The evolution is much faster. It's much less of a random walk, you know. Okay, so just to flick through vorticity field plots, right? So we started basically with that Gaussian blob, which in physical space corresponds to more or less two dominant directions, like that and like that, 45 degrees, because we started with two blobs actually, symmetrical, to have zero momentum. So then we see zonal flows forming like that. In K-space, so this is our initial condition, more or less, and then we see that it funnels itself into, you know, but with this middle kind of remaining pretty much empty. So, I mean, I need to watch time. I mean, what time is it now?
10:43.
All right, okay. So, modulational stability basically formulated in a very classical way, right? So it's more or less like in Benjamin Fehr stability of water waves, or in nonlinear optics, you know, instability of a beam, self-focusing. So we start with a sine wave, right? Okay, so with amplitude psi naught, right? So, and in this case, our frequency will be well, drift wave frequency of linear waves. So this is an exact solution for arbitrary amplitude. There is no nonlinear interaction for a single plane wave. Okay, and then we take this and impose some disturbances on it in the form of a modulation wave number and two satellites. So the minimal model is 4-mode truncation for that system. So one wave number of the original wave, one of modulation, and two satellites, K pumping plus K modulation and K pumping minus K modulation. So a very classical formulation. And so originally in this context was done by Lorentz and then considered by Gill, and to much greater degree of sort of analysis was pretty much complete linear analysis was done by Adrian Gill, very beautiful paper. And so, and who obtained the following dispersion relation, right? And also he introduced this nonlinearity parameter of the wave. Okay, its amplitude k cubed divided by beta, right? The instability changes its quality whether this nonlinearity parameter is big or small. So just for reference to say that in plasma literature, most of the works on modulation stability were in the limit m much greater than 1. M tends to infinity limit. And in fact, this limit was also, this is basically Euler equation limit because you ignore the beta effect. And in the Euler equation limit, it was done even before Gill and Lorentz by Arnold and Mishalkin. So instability of Kolmogorov flow, of instability of sinusoidal flow, and all this instability cone was obtained there. And then experiments were performed how this zonal flow that is created breaks up into the vortices, and so on. So there were some experiments by a group of Dalzhansky and I think Sweeney and So anyway, so that's kind of, so m equal to infinity is Euler limit, m equal to 0 is weak nonlinearity limit where we expect resonant wave interaction. And indeed, if we fix k to be meridional wave, okay, like where maximum of ITG instability is, for example, and then change modulation wave number, we plot this growth rate as function of modulation wave number in two-dimensional Fourier space. We see that for big values of nonlinearity, the maximum growth rate at zonal is zonal. So zonal flow is the most excited wave. Whereas if we reduce the m, then at some point we get maximum actually slightly off-zonal. Okay, it will be inclined disturbances. And for very small m, basically the whole of instability will be concentrated along the resonant curves that satisfy three-wave resonance. So that was pointed out by Gil already, so that it will become three-wave interaction dominated if the pumping wave has small amplitude. Now, nonlinear evolution also is different for different wave numbers. So basically, for different nonlinearities. So if nonlinearity is big enough, what happens? So this is now numerics, and that was done by Brandequin. And so the wave grows, and then at some point it experiences the saturation, the zonal velocity, that is what is plotted here. And if we plot a zonal velocity profile in physical space as function across it, right, of distance across it, we see initially sinusoidal disturbance grows and develops this kind of very narrow jets. So zonal jets pinch themselves nonlinearly to very narrow things. And so this actually can be predicted if the scales are separated between modulation and the carrier wave. One can develop nonlinear WKB-like approach where you can obtain self-similar solution, as I did with my paper with Manian, that predicts self-similar solutions to predict a collapse in finite time singularity formation for zonal jets. Of course, this kind of approach breaks down when scale separation breaks down when jets are thin enough. So, but this is kind of intermediate asymptotic self-similar regime of that. And so now let's look at the physical space. What happens to this basically zonal? So for large amplitude, what we see actually is so here is an initial drift wave. So this is modulation. It develops, and then the vorticity rolls up into vortex streets, right? It rolls up in vortex streets, and that's precisely when saturation occurs. And saturation persists for a long time until, due to dissipation, some further instability, like vortex pairing instability happens, and then everything goes totally in total turbulent state that doesn't remember its initial condition. For weakly nonlinear case, what happens if we do develop the zonal flow and in physical space that would correspond to vorticity being kind of focused in some regions and depleted in other, right? But then it will go back. Okay, so basically, if you think of your four-mode truncation system, right? So initial instability, you can integrate this system, and it will experience nonlinear oscillations. And initial exponential growth will be followed by decline, and then growth again, right? And so four-mode truncation system would experience infinite oscillations, right? And for small nonlinearities, this is what the system does. But of course, at some point, four-mode truncation breaks down, the energy leaks into further modes, and we create a fully nonlinear state with zonal flows. But please have a look here. Pay attention to that it's not completely zonal. The resulting statistical state is not completely zonal, right? It's slightly off-zonal, like predicted already in the linear theory. The most unstable mode is not completely zonal. Okay, and in fact, in the oceans, they recently started paying attention in observations to things that they call striations, right? So that if they measure the vorticity, okay, in oceans, they notice that it is aligned in an off-zonal, slightly off-zonal way. And in Fourier space, here is the picture, right? So that's how. Right. Okay, so I guess here for this modulation and stability part, it's you know, I think it still remains an unstudied question when it's better to use modulation and stability scenario and where one has to talk about cascades, right? And that been mentioned in a workshop last week. And to me, it kind of intuitively, so when the initial spectrum is narrow and not so strongly nonlinear, then one has a shortcut modulation and stability excitation of zonal flows. When the initial spectrum is broad, you excite with initial instability broad spectrum, then perhaps inverse cascade is more relevant. But to make this picture more quantitative, I think some work remains to be done.
Well, often in the simulations, where you have the carrier wave is unstable, so it's exponentially growing. If you start from small initial conditions, you end up with a case that the starting point is monochromatic and strong turbulence. Nearly monochromatic, like the...
In the starting point.
Yeah, and so that's not one of the two cases you said. Which should we think about there?
No, if in the starting point you have monochromatic and strong, then it's modulation instability, I would expect, right? So I mean, in the limit you can have extremely strong, beta is not important, then it's just the instability of Kolmogorov flow, right? So Arnold-Mishalkin instability. So, and one other thing, you know, so this pinching of jets, and actually there's another thing that I should notice, the eastward-westward asymmetry. So the jets, the kind of the concentrated jets are mostly eastward rather than, so is that something to look, to see if in fusion have similar effects? There must be some sort of asymmetry with respect to the direction of zonal flows, right? And maybe.
How does that arise? How does that arise?
Numerically.
No, I just mean.
Okay, so there is another thing, of course, the instability argument. So beta effect modifies the relay criterion. So in this case, it becomes a relay core criterion. So it makes waves in eastward direction a bit more stable and westward a bit less stable, right? Instead of a simple inflection point argument, you have this kind of shifted by beta, you know, criterion. Okay, well, and pinching, maybe does it look like we have some sort of very concentrated zonal jets? Maybe it has to do with you know, transport barriers being thin, you know, so.
Momentum conservation is violated.
For what?
You start off with an isometric system.
No. I mean, the thing is, the total momentum is still zero, but the jet is thin and strong. And, but they are separated by a big region of something oppositely directed, which is weaker. You see, so the momentum is still zero. Total momentum is zero. Okay, so finally, okay, well, LH transition. So this is a familiar picture that, you know, many of us heard or drawn in the past about this feedback loop, how zonal flows will, in the end, dissipate the suppressed drift waves, right? And in fact, I mean, we stumbled across that kind of mechanism, or conjectured this kind of mechanism based on wave turbulence considerations, right?
Sergey, when you say accelerate transfer, what specifically are you thinking of here?
Yes, I will explain in a second. So what I mean is that this shearing by zonal flows, right? It takes you in Fourier space faster from instability region to dissipation region, right? Wave number is increasing, and you're just transported there in Fourier space. Right. Okay. So this is the kind of picture of sheared eddy. Right. If we actually look in Victor Starr's book, I think it's on his on the cover of his book, is precisely this picture. He liked it so much he related it to the negative viscosity phenomena.
Where did you find that?
There's a book on negative.
Because I'm talking to GFD people, and they yes. Okay, and this is very very well-known book in GFD community. Okay, kind of classic. So basically, one can argue that from this shearing picture, okay, eddy scale decreases by zonal flow because cross-section is decreasing if area is preserved, of course. Potential entropy is conserved. Well, basically meaning conservation of vorticity within this blob. Therefore, energy, which is scales like entropy times L squared, right? Because they have k squared factor between them, should be decreased. And if it's decreased, it must be transferred in the conservative system to zonal flows, right? So the total energy conserved must be transferred from eddy to zonal flow. But this is wrong. This is wrong because, as was shown by Krychin in 76, if you consider a round eddy with uniform patch of vorticity with embedded in constant linear shear, you can find precisely the analytical solution for this problem, and you can find that the energy is in fact remains unchanged. And the resolution how to resolve this paradox is that actually it's not right to say that the scale is decreasing, because there's another scale here across this way which is increasing. Okay, so and some energy goes to some energy is decreasing in some scales of the vortex, but some that
Is it just because it's effectively the velocity field, this interaction between vorticity and velocity is just that you don't grad your interaction and that doesn't change energy itself?
The thing is that the energy is changing. So in Fourier space, there is transfer from some case to the others, right? But the total energy of the vortex is constant.
So you just said if you had a global vorticity and put it in the velocity field,
Yeah.
is it a different velocity field than the velocity field of that vorticity?
No, you put it. So you put blob of vorticity in a constant shear, right? Which is constant vorticity. Okay, uniformly. And this will remain like that for forever. It's kind of like it's called Kirchhoff vortex.
This vorticity is just a passive vector in this context, or is it actually?
No, this is active.
inside
No,
that
this is active vector. Yeah.
Right. So is it just so is the energy conserved simply because the Navier-Stokes interaction doesn't?
Well, yes. I mean, maybe. Well, okay. So to put it this way, right. Okay.
Well, because if I do this to a magnetic
Yeah.
field, right,
Yeah,
then
yeah.
the blob of magnetic field will increase its energy.
Yeah. No. I mean, there are resolutions here that. Okay. So I mean, all I'm saying that simple picture sometimes have to be used with caution, right? But of course there will be transfer. I mean, first that because at some point the distance across the vortex will reach dissipative scale, and then ellipse cannot get too thinner than something, right? And so this will upset this balance of energy, so it will be okay. Another thing is actually nonlinearity. Rewinding back, Sasha, to your question, I think it is assumed that it's a passive scalar, yes, in this particular case, so by Krychin, so nonlinearity was ignored. Okay, so let me just.
Is this an important result?
No, it's not important. So I want to rewind it a little bit. So I want to fast forward a bit because I mean I want to say something.
This
5 minutes, yeah? Okay, so basically I want now to check this this kind of suppression loop scenario, right? But of course, the Hasegawa-Mima equation doesn't have instability in it, right? And so, well, I either have to go to a further level model like Hasegawa-Wakatani, whatever has instability, or I actually resort to do some on a simpler level. I introduce in Fourier space. I introduce right-hand side that would with a growth rate here, a right-hand side instability linear term that with a growth rate that would that is obtained in high-level model, right? The growth rate like this. So a function that would peak at a particular meridional wave number of order of Larmor radius, okay, and that that would be 0 at 0, so it would be at large scales would be neutral, and it would be dissipative at high wave numbers. So somehow think of an island, right? So the island is positive instability, and underwater it's negative. And so the top of the island is at k rho of order 1. Okay, so and here is the result, and it's actually quite very recent. It hasn't been published yet. Well, first of all, the theoretical predictions that was in bulk myself and Zakharov, right, and that predicts the following thing, that when zonal flows are generated, right, they will suppress the small-scale waves. But if they suppress small-scale waves, right, in Fourier space, they will suppress the whole of the pumping term, because the energy injection term is proportional to the amplitude, right? So that wouldn't work if we had just right-hand side, given right-hand side forcing as a typical in turbulence simulations. It's important that it is instability, right? By suppressing the amplitude, I suppress the energy input. And this way, I achieve saturation of energy in the system and saturation of zonal flow. And now, if I do, and the prediction for that saturation is this velocity of zonal flow. So this is drift velocity. This is characteristic large scale of the problem. So let's say characteristic size of the zonal flow. Maximum value of gamma, so it must be grad T, whatever in your case. Kf rho, well, more or less of order 1, you could say. Okay, so in Fourier space, what happens is this. Okay, so we where the linear instability is active. We start with very, very low initial levels of initial data, right? And so therefore, initial dynamics is purely linear. And it will be determined by gamma. It will grow. Okay, it will be drift waves that grow according to that gamma that we put in the model. Okay, and it will grow around this maximum as indicated in the previous screen, right? Mostly here. But then at some point, when they grow enough, nonlinear interaction will pick up. There will be nonlinear wave interaction that first, will kind of spread energy along this low resonant interaction. And then there's also some predictions that I won't go into details of, which there will be a non-local interaction of scales that leads to sort of diffusion in Fourier space, not two-dimensional, but one-dimensional kind of diffusion along a particular directions, along particular curves in the Fourier space indicated here in dotted lines. And we see kind of like signs of that kind of one-dimensional type of diffusion going here. Okay, and then, well, you see a transfer of maximum from instability region to zonal region, right? And so the around instability region, it's around 50. So you have suppression, right? And we see, so in the end, we have things getting more and more large scale around zonal flows, right? And so here, this in the last graph, I show the energy of different components obtained by a cookie cutter, right? I get a cookie cutter, and I cut energy in the region of positive gamma, right? And I call it, well, wave energy, right? And then I have another cookie cutter that separates zonal and off-zonal energy, right? So I say something that with ky greater than kx is zonal, something otherwise it's off-zonal. And I plot these three energies here. So it is in a lean log scale. And so I see that initially the energy of the waves is growing exponentially, linear in this graph, right? Until very suddenly, no linear interaction kicks into place, okay? And what happens there, so this is zonal component, right? First, off-zonal grows faster than zonal, but this is pretty much the same as this, okay? Because, I mean, but then zonal component kicks in, right? And so it is greater than off-zonal here by, say, order of magnitude in this particular simulation. It kind of gets less in the end because nonlinearity is bigger and beta becomes less important. But this was pretty strongly nonlinear run, okay, I have to say. So the zonation would be more pronounced for weaker nonlinear runs in this case. But what you see here is that the suppression, so this the waves at the instability region, they drop by several orders of magnitude, okay, and they stay there low. But also you can see saturation, yeah? So, well, of course, numerically you can't say precisely it's extremely slow growth or saturation, but the theoretically predicted level based on this formula would be around 1. Okay, so it somehow agrees, with that estimate. The solid line is zonal, defined as energy of everything that is greater than 45 degrees to zonal direction.
And the fat dash is waves and the dotted?
And the dotted off-zonal, total off-zonal. So basically, let's put line like this, right? Everything here is zonal, everything within that is off-zonal. Okay, and it's arbitrary.
But doesn't it actually needs to be? I mean, in order for what's the zonal?
Well, okay, so
it's different here because it's CHM. If you had you had the funny term,
yes,
then you would have the KX.
Then you would have much stronger zonal. Yes, it would be much stronger. But I also want to emphasize here, if here beta is bigger, it would also be stronger zonal. Okay, so there are two things at work for zonation. That funny term of non-adiabatic response and beta. They kind of.
You reach saturation,
Yes. So the predicted saturation is here for these parameters of the run, and you see that you kind of you're at this point, and you see the also the sort of saturation of the small scale energy here at a very low value. I mean, how many orders of magnitude? So 2, 4, 6, 7 orders of magnitude less in energy than the zonal. So, yes, and that's it. So the summary, what I wanted to say, that it seems that CHM is still useful in spite of existence of more sophisticated models, and it can be seen as a minimal model for getting and even getting new predictions and getting sort of understanding a reference point for moving forward what to look in the other models. So But of course, one should move forward and now having gotten insight of, say, saturation levels, of particular routes of transition, and so on. One should move on to more realistic, but perhaps maybe one step at a time. So what we would like to consider is a two potential model. So, for example, Hasegawa-Wakatani, or maybe some equivalent for ITG. Okay, thank you very much.